Saucier, this is a video lesson on tangents to a circle. Let's work an example right away. Find the rate of change at x equals 1 of x squared minus xy plus y squared is equal to 1. Well, this isn't the equation of a circle. It's actually an ellipse. But it still embodies the nature of this kind of problem, to work with an ellipse. And the ellipse is a little more sophisticated so that we can have an example of using the product rule in implicit differentiation while we do this. Also, I'm not finding the equation of a tangent line in this case. If I'm asked to find the rate of change, then it will be the slope of the tangent line. But we have the nature of the project in this problem. And that is to find derivatives of something more sophisticated than a function. We could use software to graph this equation, and if we did, it would look approximately like this. Approximately. So if we're going to find the rate of change at x equals 1, then we could think we're trying to find the slopes of a tangent line to this ellipse at 1. But there's more than one intersection at 1, more than one tangent line. Therefore, more than one rate of change. Now, to find the rate of change, we need to take a derivative. So we're going to take the derivative with respect to x of this equation. Which is going to require implicit differentiation. So let's do that. The derivative with respect to x of x squared is 2x. We are differentiating with respect to x, so any term that contains only x will be simple to take the derivative of. The derivative of x times y contains y, so in implicit differentiation, we want to think of y as a function of x and apply the chain rule. This is also a product rule, x times y. So I'm going to subtract, and I'm going to use parentheses to contain the product rule that we'll produce right now. In this case, the derivative of xy is going to be the derivative of x, which is 1 times y, plus x times the derivative of y, which is 1, times a chain rule, dy over dx, because we need to consider y as a function of x. That concludes the product rule, taking the derivative of negative xy. We have to be careful to distribute the negative when working with this further. Now I'm going to take the derivative of y squared, which is 2y, and again, a chain rule because we're thinking of y as a function of x. And this is equal to then the derivative of 1, like any constant, is 0. I've taken the derivative implicitly of my elliptical equation. I'm trying to find the slope of these tangent lines, the rate of change. And that rate of change is dy over dx. But the rate of change has been expressed twice in the derivative of my function. So to clean this up, I need to solve for dy over dx, and then I'll evaluate. Solving for dy over dx in this case means that I'm going to need to distribute the negative, combine like terms, and then collect those terms that include the dy over dx so that I can factor it out and put it in one place rather than having it in two. First, let's distribute the negative and ignore multiplication by 1. So this is 2x minus a y, then minus an x dy over dx, plus 2y dy over dx. Is equal to 0. Now I'm going to move the 2x and the negative y to the other side of the equation. So on the right side, I'll get minus 2x plus y, which will cancel them here. And on the left side of the equation, I'm going to factor out a dy over dx. So what I get when I factored out the dy over dx, in this term, it will leave a negative x, and in this term here, it'll leave a positive 2y. Now I've got dy over dx in one place. I can solve for it by dividing both sides by negative x plus 2y. When I do, I will get the negative 2x plus y that's already on the right, divided by negative x plus 2y. I have an expression for the derivative of y with respect to x. The slope, or the rate of change of y with respect to x, which the problem is asking me to find. But in order to calculate or evaluate that derivative, the derivative is dependent on x and y information. What are the x and y information? It's the x and y coordinates of the points that the tangent lines are intersecting. And these points both have an x value of 1, because that's what the problem asked me to find, is the rate of change at x equals 1. What's the y value? I don't want to go with approximating it in the graph. I want to calculate the exact y value. I do that by going back to the original equation and finding y with my known value of x of 1. So the original equation is, if I put 1 in for x, 1 squared minus 1 times y plus y squared is equal to 1. And I want to evaluate y. 1 squared is 1, and if I subtract 1 from both sides, then what will remain with is a negative y plus y squared is equal to 0. Now I can factor a y out of this. I could use the quadratic formula because this is quadratic, but it's easy to factor. Out of y, I get negative 1 plus y remaining inside the parentheses is equal to 0. And I will get 0 when y is equal to 0 and 1. So to finish the coordinates of these 2 points where I have tangent lines, I've got a y value of 0 and a y value of 1. My graph is inaccurate because for this lower point of intersection, the y value has been calculated to be 0, so the tangent line should be at 0. It's a good thing that I didn't go with the sketch of my graph. I'm going to adjust where this tangent line must be intersecting to make it a little more accurate. The coordinates of this point are the ones that were calculated with the equation, 1, 0, and the coordinates of this point are going to be adjusted so that the visualization matches a little bit better with the algebra, which proves what it should look like. We're going to finish calculating dy over dx, the slopes of these two tangent lines, which has been adjusted in my present visual presentation, and they will be equal to two calculations, one for each coordinate. I'm going to do the coordinate at 1, 1 first. So the slope of this tangent line will be negative 2 times 1 plus 1 over negative 1 plus 2 times 1. Or simplified, negative 2 plus 1 is negative 1 over negative 1 plus 2 is positive 1, and that simplifies to be negative 1. The slope of one of my tangent lines is negative 1. And with this adjusted visual presentation, it kind of looks like it. The other tangent line, the second derivative, or the calculation for the derivative of the second tangent line with coordinates 1, 0 will be negative 2 times 1 plus 0 over negative 1 plus 2 times 0. I substituted the x and y values in again. Simplifying, I have negative 2 plus 0 is negative 2 over negative 1 plus 0 is negative 1. And that simplifies to positive 2. Checking my algebra, 2 is expected to be positive and approximately looks like my adjusted visual estimate.